Okay, so this is this just to let you know what this notebook is and isn't. This notebook is kind of meant to let you see how automatic differentiation is kind of magical in a way. That's kind of the real purpose. You'll start to get a bit of a feel for how forward mode works. And what I like to emphasize is to what extent this is possibly more computer science than mathematics. Like we all have this notion that, you know, what, you know, whatever courses that are now being taught in computer science that maybe used to be taught in math courses like probability, statistics, I think everybody agrees that calculus lives in math departments all over the world, right? Lots of other math subjects are being hijacked by engineers, computer scientists, and so forth. But calculus, that's sacred, right? That belongs in mathematics, right? Well, here's a case where calculus is as much of a computer science topic as it is a math topic. And I think that's kind of what fascinated me most about this. Oh gosh, I first put this together in 2017. Is it really 2023 now, 6 years later? Well, so it's an oldie but goodie, but I promise you, you'll like it just the same. Okay, and I do like to tell people that I used to go to conferences and I would hear people talking about automatic differentiation. People talked about it before it was hot. I mean, it became hot because of machine learning. But a couple of decades before machine learning, people would do it, and they would do it on the sidelines. Nobody paid attention back then. It didn't have sort of the big excitement that it has today. But I would go to conferences, and somebody would get up and talk about it, and I don't know, I would read my email or tune out or work on my own math or something. I didn't really pay attention, and so I missed the boat. I didn't appreciate what I thought was most important about automatic differentiation. And I just made I made a jump in my mind of what it is, right? And I figured it was something symbolic like Mathematica, Wolfram Alpha, we've all memorized tables of derivatives. Here's a small table of derivatives. I figured that if I could memorize it when I learned calculus, then a computer could be taught to do these things also. So maybe that's what it is. That's great. I could do it. A computer could do it better than me. Fine. I didn't care. Turns out that's not what automatic differentiation is. So then I said to myself, oh, maybe I got it wrong. I'm just guessing anyway, and I don't really care. But maybe it's some sort of numerical difference like we do to check our answers, right? And so, I want the derivative at this point x, right? So I can do a forward derivative and get the slope of the tangent, or I could do a backward derivative, go backwards and get the slope of this. I guess it's a secant to be technical, right? But the slope of this line, right? Or I could even do a central difference, which connects these two dots. And and the whole big deal, of course, is when you do that, as Stephen explained, what's a good delta? Right? In math, you want the delta to go to 0, right? That's the very limiting definition of a derivative. But on a computer, if delta gets too small, as you've seen, you get that catastrophic cancellation happening, right? And so numerical analysis is kind of about what's a good delta, and Stevens basically said that something on the order of 2 to the minus 26, which is the square root of double precision machine epsilon, is a good rule of thumb. Where you might remember that curve where the error went down like an absolute value sign as it got smaller, and then it went up again, and the best one was at the bottom, right? That's the best delta x. But the key thing that's interesting is that automatic differentiation is not this, and it's not that, right? And so what could it be, right? And the way I like to show people what it is, is I like to start with a simple example of it in action, right? And this is where, at first, it's going to look like magic, right? Nothing up my sleeve, and then I will explain to you how it worked. So I'm going to take one of the oldest algorithms, one of the oldest interesting algorithms known to mankind, the Babylonian square root algorithm, which I think maybe you've all seen, but if you haven't, you start with a guess t to square root of x, right? So I've got a t, which I'm hoping is close to square root of x. Now, right, and if I take t and x over t, right, if t was too small, x over t, of course, will be kind of on the large side, right? If t was a guess that's large, between t and x over t, one's on the large side, one's on the small side. So why don't we just take the average, right? And then this is something we could keep doing, okay? And that's the Babylonian algorithm that converges to the square root of x. Okay, very simple algorithm. It was known for thousands of years. How complicated, could it be? But I still think it was pretty clever, the Babylonians. I mean, They didn't have Julia. I mean, I thought it was pretty clever. So in any event, I'm going to, just for simplicity's sake, I'm going to start at 1 for no reason, because I'm just doing an example. So I'm going to start at 1, right? So I have 1 and x over 1, and I'll take the average. And then by default, I'll do 10 iterations of t plus x over t over 2, right? So, even if you don't speak Julia, I think this algorithm is easy to understand. It's an input x, and by default, we run 10 times, but you can give an argument and make it run more times. Okay, and so let's go using forward diff, and let's take the let's let forward diff do it. And of course, we, with our modern view of the world, we know how to take square root, right? Everybody in this building, everybody in this institute could take the derivative of square root. It's 1/2 over the square root, and so we get the derivative. But before we do that, let's actually make sure that the code works. Let's actually check the Babylonian algorithm that I wrote. So here's the second one is Julia's built-in square root of pi, and here's the Babylonian calculating the square root of pi. And I guess this is pretty convincing that the Babylonians knew what they were doing, right? I mean, we could do the same thing with 2, could run the Babylonian algorithm, except for some little bit over here. Maybe the last bit, we basically get the same answer with Julia's built-in square root and the Babylonian algorithm. Okay, and let's skip this for a minute. Okay, and I think that's not important. So just checking the algorithm for the moment, not even the derivative. So I'm actually gonna plot a few iterates of the Babylonian algorithm, just so you can see. So the first iteration, maybe you remember, was 1 plus x over 2, right? I still want to call this a linear function, but in this class I have to call it an affine function. I don't know what the real terminology is. When do I get to say that a first-degree polynomial is a linear function? I think there's a context as to whether I'm calling it a map or a function, right? But any event, this thing's a line, however you want to call it, right? The first step of the Babylonian algorithm, iteration 1, is given x, compute 1 plus x divided by 2, and that's a first-degree function, right? The second iteration, I'm plotting it, is here, right? And then it gets closer and closer to the sideways parabola, which of course is the square root. In fact, by iteration 5, you can't even see much of a difference with your eye, right? So iteration 4 is the purple, and iteration 5, you can't even see it because the black parabola is on top of it, right? And so just to kind of convince you that the Babylonian algorithm works. And anyway, I like Plotly. I love doing this all day. I can go left and right and look at these numbers. I love this. So I like interactive things. Okay, now what I'm going to do is let me see how many, I changed this over the years, so 3, 4, 5, 6. In about 9 lines, I'm going to create a function that will calculate the derivative of the Babylonian algorithm. And nowhere will I teach it like 1/2 over the square root of x, right? I will not do that. You'll see there'll be no finite differences, and there will be no symbolic, I'm not, and it's going to be by magic, but we're going to get the right answer. So you ready? So I'm going to do it in 9 lines. Here's 3 lines. I'm going to create a Julia type. I'm going to call it capital D. Later on, maybe some of you have heard this word. D is for dual number, so that's why we're going to use the D. And we're basically going to keep a function derivative pair, an ordered pair. And so this is nothing but a container to be able to keep 2 floats, right? But which floats am I going to keep? I'm going to have the value of a function at a point and the derivative of that function at a point. All right, I've used up 3 of my 9 lines, and everybody agrees there's no finite difference, no symbolic answer, right? So I've got 6 more lines here. Oh, here, this is, let me just show you what I've done here before I do anything else. So if I want to create one of these objects, so I would have to put in a tuple like d of 1, 2. This line lets me remove the parentheses, which are I just find them annoying. So this line doesn't count. But you see, I've got this dual number. It doesn't do anything yet, right? I can't add dual numbers yet. If I try, it gets mad at me. Look, plus not defined. All I can do is define a dual number. That's it. It's just a pair of numbers. Okay, can't do anything at all with it, right? Um, Other than store it, right? Um, but here, what I'm going to do is create a few. Oh, I don't need this greater than. That's why I could have one fewer line. You know, I'm going to comment this one out. I think somebody once asked me, you know, to define it for greater, but yeah, I don't need this line. So I'm actually going to have 3 plus 5, 8 lines. Okay, so let me tell you about these next 5 lines. Mainly, I want to define add and divide on a dual number. I don't need minus and times yet, because if you look at my Babylonian algorithm, if you remember the algorithm, where's the Babylonian algorithm? I do a plus and a divide and nothing more. Okay, so for now, later on I'll add times and minus, but I don't need it yet. So I want to define a plus and a divide. So in Julia, I don't need this one either. This thing could go away. In Julia, if you want to overload plus and divide and a few other things, you have to import it from base, right? So this is just like a Julia detail thing that says, give me permission to redefine plus, right, and divide and a few other things. And what do I want to do when I plus a couple of dual numbers here? Let me just do this one only, just so you see. I'll execute only the plus. Okay. Now I can add dual numbers, and it's just going to be like adding vectors, right? So I'm just going to add the first element of the tuple, 2 and 3, and the second element. Okay. So now I can add tuples, but I can't divide them yet, right? So this dot notation, this broadcast or pointwise notation, says that basically add the two parts of x and the 2 parts of y like a vector. Okay, so this adds 2 and 3 to get 5, and 3 and 4 to 7. All right, now let me bring in the divide. I can't divide yet, by the way. I could try, but it'll get mad at me. You see. Ooh, I must have executed it. Oh, did I execute it? I'm sorry. Then it took away my. Well, whatever. All right, I guess I must have executed it, so I'm not getting away with it. But here, it doesn't matter. So here, this is 2 divided by 3 is 2/3, but notice this isn't 3 divided by 4, right? So I have a different rule for. So the add rule is just adding up like a vector, but the divide rule is a little more complicated.
By the way, Alan, did you want to share your screen on Zoom? I forgot about.
Oh my gosh, I didn't share my screen, so you don't see a thing I've done.
I can see it behind you on
Oh, that's funny. Okay. There we go. All right, better? All right. So, right. So, divide. So everybody, of course, remembers the quotient rule from calculus. When I think of it, I hear my math teacher singing it. It wasn't just like, I mean, I'm not, like, there was like denominator times the derivative of the numerator minus the numerator times the denominator of the denominator squared, or I don't know. Did your teacher sing it to you, or how did you sort of memorize the quotient rule? Anybody have a good song for it? Anyway, you know, you drill it into your head, right? V du minus u dv over v squared, or denominator denumerator. I mean, I don't know. You may have heard it different ways, but you all know it, right? Yx, this thing over here, the quotient rule. Everybody knows it, and so. I'm just extracting the parts from, y is the denominator, and so this is, 1 is the value, right? So this is the denominator, right? X is the numerator, so this is and 2 is the derivative. So it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. Okay, so that is what I'm going to teach. I'm going to teach Julia how to essentially add derivatives, which is just add, and how to divide derivatives, which is just, the formula just applied at a point, right? And so this division is using all 4 numbers so that it can get the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared, you see. Okay, and that's what this 1/9 is. All right, that's it. Just these 3 plus, what did I say? 3 plus, I haven't told you about convert and promote. These are a little bit more sort of technical details. But do you know how, if you add a complex number in a real, right? Like if you go 3 plus 4i and you add 7, right? Now, what's really going on is that that 7, in some abstract sense, is being converted into 7 plus 0I, right? And then you add the real parts and the imaginary parts, right? Everybody does that all the time, right? So we want to do that sort of thing where um, if, if you have a real number, we want to think of it, if you have a scalar, we want, in effect, a constant is really what's going on here. We want to think of this as the constant x, where the value is x and the derivative is 0, right? And we want that to be kind of automatic because it would be nuisancey to type it all the time. So that's what that does. And then the promote rule says that if you give it a number, you should, when you see it in the context of a dual number, everything should be promoted to the dual number, just like it happens with complex numbers, right? Where, like I said, 3 plus 4i plus a real number, you would add, you'd put that 0i, in your mind or on a computer, but you would promote everything into the complex land and then do the addition. Okay, so those are two necessary things, and now let me go ahead and run the Babylonian algorithm. And I am, without changing the algorithm, remember the algorithm takes a scalar in. Let's see it again, let's find it. The Babylonian algorithm, which is up here, it takes a scalar. I'm not going to rewrite the algorithm, I'm just going to feed it something new, something different from a scalar. I'm going to feed it a dual number. And so let's do it. Where did it happen? Here. So I'm feeding the Babylonian algorithm 49, comma 1, right? So this is like this is how you seed we'll talk more about seeding the start of the story with the number 1, or if it was matrices, it would be the identity. And we get the square root being 7. Yep, that's good. The square root of 49 is 7, right? And the derivative, which you all know, we can let Julia check it for us, is 1/2 over the square root of x, is this number right here, right? So whatever 1/2 over 7 is, 1/14 or something, right? So this is the number 1/14, right? And you should be astounded by this, that I took an original piece of code without a rewrite, and I fed it this funny kind of argument, and all that argument did was it knew the quotient rule and it knew the sum rule, and I got the right answer for the derivative, not symbolically and not with finite differences. Okay, isn't that amazing? Like that's even possible? Like, wouldn't that blow your calculus teacher's mind that this could happen, right? Here's another example where I do it with pi, just in case 7 wasn't convincing enough. So this would be the square root of pi and 1 over 2 square root of pi, and this is the way done with Julia. And you could check the numbers. You see it all works. And in fact, what you can do is actually look at what's happening is the Babylonian algorithm was an iteration, right? And so somehow this square root is the result of an iteration. We do 10 steps of an iteration. And so at each time, we must be getting closer and closer to the derivative. So just like we get closer to the square root, somehow by feeding this in, we must be getting closer and closer to the derivative of the square root. And in fact, I could plot each step of the algorithm. So remember, the first algorithm was first degree. I still want to say linear, but I'll say first degree. And so its derivative, of course, is a constant, right? It's just the constant 1/2, in fact. So there it is. And here are a couple of iterations, and I also plotted 1/2 over the square root of x, the true answer, the reciprocal of the parabola, in effect. And you could see that it's heading closer and closer, and pretty quickly the eye can't even see it. So this doesn't explain to you how it works, but maybe it kind of adds to the convincing nature of the fact that it does work, right? And it's still mysterious. I could say a little bit more. I'm going to tell you how it works. But before I do, I like to show off a few things. I don't know how well this works these days. But I do like to tell people that in Julia you can see assembler. Nobody reads assembler. Anybody here read assembler? Anybody here actually, you do? Or have, or a little bit? One person is willing to admit that they do it a little bit. Some computer science classes at MIT teach you this stuff. Most people never look at this, don't want to look at this. The thing that I like to just mention is that in Julia, the assembler is short. And so this is the assembler for this derivative code, this kind of derived code. And short assembler is more or less correlated with fast code. And so not only does it get the right answer, but this sort of game is also quite fast in Julia, right? And that's kind of a nice thing to be able to have. Okay, so I'm still not going to tell you how it works, but I'm going to grab SymPy. This is Python symbolic program. There's a Julia symbolic program, but I don't completely trust it yet. Maybe it's ready for prime time. But I did this originally with, I wrote this before there even was Julia symbolic. And anyway, it just worked so well, I would take it. And so one of the things that's sort of interesting is to ask, how should I say this? I'm going to tell you something that's mathematically equivalent to what we're doing, but I don't want you to get the impression that this is how it's computed. So let's talk about not the derivative yet, but just the Babylonian algorithm. You remember that this is the function at the first step, x plus 1 over 2. I can use Julia's ability to overload to run it on a symbol x, and then I could see what there is at the second step or at the third step. And so in a way, at the, whatever this is, if this is the first step, second, third, fourth, fifth, at the fifth step, the Babylonian algorithm exactly computes this rational function. It's a 16th degree polynomial over a 15th degree polynomial. But don't get the wrong idea. Nobody in the real world is calculating the coefficients of this polynomial. I mean, these coefficients, we wouldn't want to store them. They'd be unwieldy to work with. But as a mathematical sense, the fifth step of the Babylonian algorithm is calculating exactly this function. And the plots tell us that this crazy function, the 16th over 15th degree polynomial, is not a bad approximation to square root of x, at least visually on the graph, right? So this is pretty good for square root of x, right? That's what we've seen. We could talk about where it is good, where it isn't good, but the point is that what it's computing is this function. And we could do the same game for the derivatives, right? So the first derivative here is the coefficient of x is a half, that constant, and we can see what's being computed exactly here. And this is a ratio of 30th degree polynomials. And again, I want to stress, we are not, I'm just building this up just for fun. We are not in the algorithm getting literally these coefficients. They're too big anyway for working with. But in a mathematical sense, the fifth step of this derivative Babylonian algorithm is calculating exactly this thing. And so this has to be some sort of approximation to 1/2 over the square root of x, the derivative of square root of x, right? This is what that is, okay? So let me get a little closer as to how, now you must be wondering, I hope you're all kind of sitting in your seats saying, how is this working, right? What's happening here? And to get you a little bit kind of closer, let me do what people used to do in the old days. People used to take derivatives of functions by hand. Before this became automatic, people would take derivatives of functions by hand. And so I'm going to do that for you here. I'm going to create a D-Babylonian algorithm, the derivative of the Babylonian algorithm. And you'll recognize that this line and this line are the original algorithm. And below it, I'll create variables. I'll create derivative variables, t prime, right? And so t prime, the derivative of this is, of course, a half. The derivative of this line of code, well, what is it? It's the t prime plus the denominator times the derivative of the numerator, which is 1 minus x, times t prime over t squared, right? So if you check, this is the ordinary calculus derivative with respect to x, right? So t prime is the derivative with respect to x, right? So this is the ordinary calculus derivative. And we're doing that at each and every step, right? And people used to do that by hand. That in other words, you don't take the derivative analytically of the big thing. Rather, you take the derivative of each line of code, right? And then you have faith that if you do that, you'll get the derivative of the big thing that you wanted on the outside. And you'll see that, of course, it works. Adding these couple of lines of code with just, this is now scalars, right? There's no dual numbers here, right? This will give me 1/2 over the square root of pi. Just by taking the derivative of every line of code, right? And so you might realize that this is actually an iteration for the derivative of square root of x, right? That an iteration that we stop it at 10 by default. We could take more steps, but this is an iteration for the derivative of square root obtained completely by taking the derivative of every line, right? And so that's kind of what happened. And so when I take the Babylonian of dx1, in effect, I am using the magic of Julia's ability to do dispatch and overload and all those fancy words, but to use simple English, I am using the fact that I don't have to rewrite the code to get the derivative. I just need the code to know the rules of taking derivatives of every operation that more atomic operations at the lowest level, and rely on the computer to piece it all together, right? Because humans are really bad at this sort of stuff. They make mistakes all the time. It's worse than long division, right? I mean, no matter how good you are at long division, humans are just make mistakes. We just do, right? And so the trick is, if you wanted to teach a computer to, if you want to get the answers to a division problem, we humans have taught computers to do the division for us, so we don't have to, right? And this is what's going on with automatic differentiation. We teach the computer to do the atomic steps, and then let it just go through the motions, okay? And so, the derivatives it goes in before the JIT compiler, and we get efficient code. So there's a notational trick which is rather nice, which is instead of taking the dual number, which is AB, we can write A plus B epsilon. And in effect, what we're doing is the same thing that, on the first week of class when Stephen said, oh, let's just write everything as like, A plus B dx, right? Just write everything to first order. Right? Physicists do this all the time. They write everything to first order, and they throw away higher order terms just all the time. So in effect, what's happening on the computer is we're treating every computation as a first order computation. And then the basic rules are, let me just see, there was one version of this was broken, but let me see if this is right. I think this is the right version. So the basic rules, every computation on a computer that's ever been written always can come down to plus, minus, times, and divide. Right? Even square root is implemented somewhere as plus, minus, times, and divide. So in effect, if you wanted to do, you could basically you can get automatic differentiation just by having these basic rules. Right? This is all you need. Now, as a matter of practice, we try to intercept it all. We're happy to teach sine and square root and cosine because, who wants the, whatever method is being used to compute the sine, and it's not Taylor series, by the way, but whatever method is being used, we don't want it to go through all this work, so we teach it things. But in principle, all you need are these rules, and you can take the derivative of anything in the world on a computer. Right? This is all you need. Here's the sum and minus rule, the multiplication rule, which, if you look at this right, maybe if you squint correctly, this is the UDV plus DUV rule, right? The product rule that you all learned in calculus, and we kind of repeated it in its matrix context in this class, right? This is UDV plus VDU, and this is the quotient rule. This is denominator times the root of the numerator minus numerator times the root of the denominator over the denominator squared. Right? It's just kind of rewritten in this first order kind of notation. But these are rules that you all learned in first year calculus, right? And I'll even point out that you could do this symbolically, just in case you don't even have to remember the rules. You could actually derive the quotient rule on the computer by just this says. Basically, take a series around epsilon equals 0 and give me two terms, please, no more. So just give me to the first order in epsilon. And here you see you get the quotient and the quotient rule from calculus, right? So this is one way to get your hands on that. If you wanted the product rule, I guess I could have just done this, right? And you get the UDV plus DUV rule, right? So that's how you can get the rules. So I'm going to do something fun. I am going to tell Julia, this is Julia magic that says to print a dual number with epsilons. And so now when I type a dual number, you remember it was just with the D's. Once I execute this command, I could see it in a way that's nice and human. So I told you this was a function derivative pair, but you could also think of it, if you like, as a first order expansion of it could be a first order expansion of a function, right? It could be the first order expansion of x squared, around x equals 1. Okay? So let's go ahead and add these last two rules. And remember, I only did plus and divide. I might as well add this seems like a good time to do minus and times, right? And you see that if I do the dual number 1 and 0, I get this. If I if I, well, actually, let me ask you. I'm not going to hit enter yet. Tell me what I should see when I hit return before I do it. Who's quick? What's the first thing I'll see before the epsilon, and then what's the? Let me start with the 0th order term. What will I see? Just shout it out. 4. Okay, and then what's the next term? 2 times 2, 4. Yep. So 4. All right, you guys got it. Okay, and this is, I changed the output. I might as well go the whole direction. Why don't I make the input also? Like t01, I'll call it epsilon, right? And so now I can actually input epsilons too, not just see it as an output, but I could do it as an output. So epsilon squared, of course, is second order, so we just get rid of it. By the way, just something fun. I actually never defined how to square. You'll notice I defined times, but I never defined square for a dual number, right? But this is sort of a little bit of a lesson, but a good software system would be one where when you square something, it actually replaces it with the thing times itself, so that a matrix square is a matrix times a matrix, and a scalar square is a scalar times a scalar. And in Julia, for whatever reasons, a string times a string is a concatenation of the string. So string squared, I don't even know if this works anymore. I have a feeling it doesn't work anymore. It's not a number, right? This is going to fail. But it shouldn't fail. Actually, I think this is going to fail. Oh, it doesn't. Oh, no, forget it. It does work, right? So multiplying two strings will concatenate them, and squaring it concatenates it, right? And so if you have sort of like a novice computer system, every time you have another type, you define another square. But if you have a good computer system, then the square inherits it from multiply, and then you just have to define multiplication. Okay. What should I get here when I go 1 over 1 plus epsilon? And again, nothing symbolic. This is actually happening completely numerical, by the way. But what should I get when I hit return? What should I see? Anybody? You're smiling. You think you know the answer?
I guess that it's written there now.
So I'll give you a hint. What's written there is not what you'll see.
1 minus 1.
Yeah, how would it appear? Just read it to me how it would appear.
I guess 1 plus or minus 1 epsilon.
There you go. 1 plus minus 1 epsilon. You could have just said 1 minus epsilon. I would have accepted that. All right? And doesn't that look like symbolic mathematics? But it's not. This whole thing happened through these dual. It's all numerical, right? There's nothing symbolic at all. It just. And this is another thing that people are saying, that there's becoming more and more of a blurring between the symbolic and the numerical, and that numerical stuff is starting to look more and more symbolic, but it's not symbolic. All right, what's the answer here? I'm not using any weird packages. Everything that I'm using was defined right in front of you, right? I'm not using forward diff or anything. Everything here is just pure, simple Julia. You saw it. There's nothing up my sleeve. What should this answer be? Sorry? You're right. 1 plus 5 epsilon. Okay, and this one unfortunately won't work. Oh, it does work. Oh, that's amazing. I don't know why that works. All right, never mind. I didn't think we could take negative powers, but I guess we could. All right, I'm going to stop. You could do this with nth roots. You could do lots of other things. But I think this is a good time for a break, and you guys get the right idea. That so now you're starting to see that if I were to summarize, and I know it's still a little bit magical, but I think you at least see that roughly how this works, is that one way or another, we're giving the rules of plus, minus, times, and divide, and we're writing programs, and then these programs are, in effect, they're not really rewriting themselves. What's really happening is that every time you execute a plus, and minus, times, and a divide, it's doing not just the basic operation that you'd all expect, but it's also carrying along the derivative as well. And the way Julia works, Julia will actually look at that divide and say, I'm not dividing scalars, I'm dividing dual numbers. Or if it sees a star, I'm not multiplying. How does Julia know what to do? When it sees two matrices, matrix, star, matrix, it knows, because it's a matrix, to do matrix multiply. So here, when I did dual numbers, I taught it to do this dual number thing. Right? And once Julia knows how to do it, it'll just carry all the way through, right? And in effect, this is really the magic of great software, where you just can define some atomic operations, and the whole thing kind of composes itself almost by magic, right? And in a way, it's almost opposite from what we teach students in a lot of classes, where we want to teach. The old-fashioned thing was to teach a student to carry through every operation and be really competent at it. In a way, the modern world is to teach students how to not have to think, rather how to build a system that is so simply designed that it just works, right? And that's, and actually to build a simple system is what takes the real human cleverness, if that sounds not like some sort of contradiction. But that's what it takes. All right, let's take I'm a little late for the break, but after the break on the blackboard, I'm going to go into more detail about forward and reverse mode automatic differentiation.